we talk about the force, the gravitational force between two masses, we've said this, and I'm going to say it again, try to say it as clearly as possible. When we talk about a planet, let's say Earth, Mars, whatever, and we talk about a satellite or a car in outer space, which there is one, we talk about the force between their centers. We haven't really explained why it's the force between their centers. But we just say, and that's okay. I mean, we just say it's the force, the gravitational force is the force between their centers. That's important to understand, right? It's like, it's not the force between their surfaces, etc. But in reality, Newton's law of gravitation is really written for what's called point masses. And so what that means is that we are saying that a spherical, and we said the force between two masses that are spheres. We said that they're spherical. We said we treat spherical masses like they're point masses with all the point at their centers. So we're really saying that this situation is the same situation as this one, where Earth is really a teeny tiny one-dimensional mass at that point, and the satellite is a teeny tiny one-dimensional mass at that point. Let's call it SAT for satellite. And therefore, for point masses, we know that's what Newton's law of gravitation is written for. It's for point masses. And we didn't write this down, but we can call that R. Whoops, R. Call that R. So we're saying that spherical masses act as if they are point masses with all their mass at the center. So we know that Newton's law of gravitation is for what's called point masses. What that means is that we are treating it like it doesn't take up any space, that it's a one-dimensional point, all the mass is at a point. Or we treat it like, a small mass. Small mass is approximated as point mass as well. Okay. Things we said is that in order to treat it like a point mass, it has to be a spherical mass. In order to treat it like all its mass is concentrated at the center, it has to be a spherical mass. So we haven't proven that, and that's what we're going to prove or talk about with Newton's shell theorem. But first, let's just in general, in order to talk about Newton's shell theorem, we need to talk about what it means to talk about the force between a point mass and an extended mass. So, for example, here's 2 point masses. It could be a car, which is treated like a point. Whoops, that point was meant to be at its center, not its eye. Right, smiling. A car and a person, right? A person. There's going to be a gravitational force between any two objects. We just treat them like points. But the only time we can treat them like points without error is when they're spheres. What if they're extended mass that's not a sphere? How do we deal with that? So we can talk about the gravitational force of attraction, for example, between 2 meter sticks. They're not spheres. We could treat them like points, but that's only an approximation because they're not spheres. So let's start with, and typically we're just going to talk about a point mass and extended mass. So this is an extended mass, meaning we can break it up into a lot of little point masses, but it's an extended mass. So let's talk about the force of attraction between, let's start with the concept. I'm not going to actually do this problem out right now, but the concept of the gravitational force of attraction between a meter stick and a point mass. Let's just start with that concept. The problem that we'll do out is going to be a slightly easier problem. Not that this is a terribly difficult problem, but the concept is basically that that the meter stick, right, this guy right here, is an extended mass that we can break up into little points, which we just did on the last page. We can break it up into little points, so we can treat each of these as a point. So the gravitational force of attraction between M1 and M2, we can break up M1 into little pieces called dm, and each dm is a distance r from, and I got to be careful, I guess let's just say r, let's call the first dm r1 from M2. Because look, let's say count down 1, 2, 3, 4, 5. I've drawn 6 DMs. We could break this up 7, 8, 9. How many? I don't know. An infinite number of small DMs, but we could take the meter stick and say, 1 centimeter is enough, so maybe there's 100 of them. But let's go down 1, 2, 3, 4, 5, and I didn't draw 100 of them. But let's go down to the 5th DM, right? this, let's draw it in purple. This one here, right? This one here, the little point mass, we're treating it, it's approximately a point mass. That is also dm. They have the same mass because we've broken up the meter stick in, the meter stick, well, we do have to understand that the meter stick has a constant density, and we're breaking it up into evenly distributed pieces. So each piece has the same mass, but it doesn't have the same distance. Right? This distance is going to be R5. It's the fifth mass, R5, and R5 is a little smaller than R1, right? But anyway, and that's okay. So what is the gravitational force of attraction between the meter stick, M1, and the point mass, M2? The gravitational force of attraction is going to be between any one piece, dF, the gravitational force of attraction between the first piece, dF1, is going to be G, dm, the mass of the piece, the mass of the point mass being attracted to it, divided by R1 squared. And that is going to be in the radial direction from the first piece. So we just call that R1 hat. So that's in this direction, right? That's the R1 hat direction. And so then we do that for all the little pieces, right? So dF5, dF2, dF3, dF4 is G dm, gmm over R5 squared in the R5 hat direction. And so what's the net force? The net force is just the superposition or sum of all these forces. So the net force between M1 and M2 is equal to the sum, that's the sum sign, of all of our little df's. And so we can just say df sub I. But it is a vector sum, and all of our vectors, right, point in different directions, depending on which dm it is. So it's not a trivial sum to do. We're going to sum these up. If we break the meter stick into small enough pieces, then the net gravitational force between, rather than me writing M1, M2, F1 on 2, the net gravitational force that the meter stick has on the point mass M2 is going to be the sum of all the df's, which is an integral. Integral of df. It's going to be the integral of all of our df's. That's an infinite sum, right? If we break it up into small enough pieces, it's an infinite sum. And so it's going to be the integral of G dm M2 over R, and now R is a variable, and R hat, yeah, so there, that's what it is. And we would go from the top of the meter stick to the bottom of the meter stick. So we'd go from, for example, if this is the y direction, let's say that's the y direction, we'd go from 0 to 1, right? From y equals 0 to y equals 1, or something like that. We'd have to integrate along the meter stick. And so the difficulty here, the difficulty with this problem, F1 on 2, which we can do, it's done in the book, I'm just not going to do it out right now, is that we've got a bunch of things, a couple of things that vary. We can pull out the constants, right? G and M2 are constants. G and M2 are constants. The variable of integration is dm. Oh, and I did what I often do, is I left off the squared, because this is a force law, not energy. The variable of integration is dm, so that has to stay in the integral. R is different for all our little pieces, so that's a variable. And R hat, the direction, we have to take components of these things. That's a variable. And so we have to so how do we do this kind of integral? How do we do this kind of integral? We have to make some kind of substitution that relates R squared, R hat, and dm, that puts it all into one variable. And actually, I'm tempted to finish solving this problem, but let's just think about, first of all, how we deal with the vector nature of it. The vector nature is sometimes the hard part. In this case, you should be able to see, only because I didn't tell you, I guess I had to tell you how far, let's say, like the perpendicular distance, we would have to give you a perpendicular distance as a reference point. How far away are the two masses? We never said. We just said that the individual points are all different distances away. But let me just do some hand wavy stuff and say, look, the force due to the one on top, the force due to this one is pointing in that direction. The force due to the one on the bottom is pointing in that direction. Those two vectors add to point along the horizontal. Those two vectors add to point along the horizontal. I'm trying to draw a color you can see. Just use a highlighter. So those two vectors add so that they're along this horizontal. And so the vertical components cancel and the horizontal components add. So we can take just the x components, right? Y is in the downward direction. X, we could say, is in the left direction. If this is plus x, we could just take the x components because the y components all cancel. Because if I have a vector pointing like that from one DM, I'm going to have a vector pointing like that from the other DM. Those two will add so that because they have components that look like that and that and that and that. So the y components cancel and the x components add. So really all we need to do here is we need to have an angle theta, and that angle theta is going to vary as we move down dm, but this is going to end up being g m2 integral of dm over r squared cosine theta. That gives us the x component. All we care about is the x component. We don't care about the y component. But we still have three variables here, m, theta, and r, and we have to relate those three variables. I just wanted to set up this problem, and now, and you could do that. You could relate these three variables doing geometry on this problem, but instead I'm going to do a slightly easier problem. Let me just say, so then once we relate those three variables, we could do this integral, and then you would get the net force, which is in the plus x direction. Okay, let's just do a slightly easier problem. Instead of a meter stick, let's take a hoop. Let's take a hoop. What is the gravitational force between this hoop, which has a mass of m1, I'm giving a little bit of dimension, and a point mass, m2, which is a distance from the center of the hoop. From the center of the hoop, we'll say that distance is p. P for Peter? I don't know. And the radius of the hoop, we'll call the radius of the hoop, rather than calling it r and getting confusing, let's call it s, radius of the hoop. Okay, this is in three dimensions, right? The point mass is above the plane of the hoop by distance p, above the center of the hoop. Okay, so how do we solve this problem? What is the gravitational force of attraction? I won't write those words, but what we do is we take this hoop and we break it into little pieces dm. And this is what we do every time we do a continuous mass problem. Break it into pieces dm and say, that piece dm is a distance r, is a distance r from m2. And the beauty here is that with a hoop, the r is the same for any dm. So that's why I'm doing this, so we don't have to have so many variables. So this dm, right? This dm has a distance r. It's in three dimensions, so it doesn't look right, but it's distance r, right? So in a side view would be, here's the hoop, and the object is above the center of the hoop by a distance p, with this being s. Okay, so each dm is r from the hoop. And then in the same way as before, right, the force of attraction from any two opposite sides, right? So let's just look at this dm here. We'll just break the whole hoop into dm's. Let's look at this little piece here, which we treat as a point mass, which is diametrically opposite from the first piece. The piece on top is going to have a force which is in this direction. The piece on the bottom is going to have a force that's in this direction. Those two pieces are going to add so that only their x components matter. So we've got an x component and a y component, and that's for the one on top, and draw a different color. We've got a x component and a y component for the one on the bottom, and the y components cancel and the x components add. So all we care about are the x components. And the x components, let's draw this here. I could have drawn, I just realized when I drew this in two dimensions, instead of three dimensions, side view would be like this. Side view. Here's my mass M2, and here's my mass M1, just a side view of my hoop. That's a hoop, not a meter stick. Okay, M1. So now let's take that little dm that's on the bottom, this little dm that's on the bottom here, that's at the bottom of the hoop, and that's some distance r from M2. The little dm on the top of the hoop, that's some distance r from the hoop. And notice all your r's are the same no matter what dm you choose. And the force, the gravitational force, is going to be along those lines, but we only care about the x components. So all we care about is this angle theta, and we can say that df, due to any dm, is going to be g times dm, that's part of m1, times m2 divided by r squared, and then we just take the x component, cosine theta, just the x component, because the y components all cancel. So that's the contribution to the total force from any single dm. And then we can go ahead and take the integral of both sides to find the net force. The net force is, and we don't even bother looking at the vector nature because it's in the plus x direction. If this is plus x, it's in the x direction, right? All those forces are going to add up to be along that center line. So we got an integral, and now we're going to do this integral. We're going to do this integral. So so this is the magnitude of the net force. The direction is in the plus x direction. The magnitude of the net force, we can pull out the constants. G, M2 is a constant. Now R is a constant because R doesn't vary for any of the dm's. Now R was not a given variable. S and P were given, but there's a relationship between R, S, and P, right? S is here, P is here, and R is here. So R squared equals S squared plus P squared. So we know what R squared is, right? That's the Pythagorean theorem. So we know what R squared is. And it's a constant. It doesn't change for any of our dm's. So integral, and theta. Theta doesn't change for any of our dm's. See, where it did for the meter stick, theta is the same. Doesn't matter which dm we choose, theta is the same. So we can pull the cosine theta out. Again, theta is an unknown currently, but we can pull the theta out, and we're only left with the integral of dm. That makes this integral a lot easier because we're only everything else is a constant. We're only left with the integral of dm. With theta, right, we can say, oh, look at the geometry of the problem. Look at the picture, the side view picture. Cosine of theta is equal to adjacent, which is P, over hypotenuse, which is R. But R was the square root of S squared plus P squared, because again, we have to put everything in terms of the given variables were simply M1, M2, S, and P. That means we have to put our answer in terms of M1, M2, S, and P. The gravitational force between the hoop and the point mass must be written in terms of those variables. So cosine theta is P over the square root of S squared plus P squared. That's just solving for R and plugging in. So those things are known, right? So theta is known, or cosine theta is known. And then we are almost done. We just have to do the integral. So let's do a plug-in, g m2 over r squared, which is s squared plus p squared, times cosine theta, which is p over the square root of s squared plus p squared, times the integral of dm. What is the integral of dm? We're just adding up all the little masses as we go around the hoop. And so the integral of dm is all those dm's added up. It's just equal to m1. Right? So the integral of dm is equal to m1, and so therefore the magnitude of the force is gm2p over s squared plus p squared times the square root of s squared plus p squared times the integral of dm, which is just m1. So it's gm1 m2 p, and then we can simplify the bottom by saying it's s squared plus p squared to the first times s squared plus p squared to the half. So that is s squared plus p squared to the, so that is s squared plus p squared to the 3/2. That's the magnitude of the force between our ring and our point P, which is above the center of the ring by and a point mass, which is above the center of the ring by a distance P. That's the magnitude of the force, and it is in, if we define our directions, I guess we can just say toward the center of the ring, because we can do it without defining an axis. That is toward, the force on M2 is in this direction, toward the center of the ring. I guess that's the direction of net force. That's the direction of the net force. Okay, that's how to do a continuous mass distribution. This is the easiest one to do because everything was constant. Like the one problem we started with, it can get a little harder. How do you get an elephant into a fridge? Probably heard this one when you were 5. Insert open door, insert elephant, closed door. How do you get a giraffe into a fridge? Open door, remove elephant, insert giraffe, closed door.